Assalamualaikum students. Today our topic is total internal reflection of light. So previously we've studied about the refraction of light, how it occurs and what are the conditions for refraction of light. Today we're going to look into this equation, this figure first to understand the total internal reflection of light. Okay. First we will consider this figure. Okay, this is a very basic figure for refraction of light. This is the incident ray after striking the boundary between two medium. It gets refracted through an angle theta r, which is greater than the angle of incidence. Okay, that's a pretty simple thing. And I have drawn this arrow to show the reflected ray. Actually, there's no reflected ray. I have just drawn it. It's an imaginary ray, so that we know that if there would be any reflected ray, then this would be its angle and this would be its direction, just to show if there would be a reflected ray. Okay, so there's a very simple thing. Now, what happens if we just keep increasing this angle theta I, or the angle of incidence? If we just keep increasing this angle, then a certain condition would be reached where if the incident ray strikes the surface at the point of incidence, the angle of refraction would be 90 degrees to the normal. You can see here, this is the incident ray, this is the refracted ray, which is 90 degrees towards normal. Okay, so and this ray travels on the surface of the medium. This ray would travel on the surface of the medium. So now an interesting phenomenon occurs. Okay, in such a case, this theta will be called as the critical angle. The angle at which the refracted ray becomes 90 degrees to the normal is called the critical angle, and it is denoted by C. You must have noticed that I have not written theta I here, because in this case the theta I becomes theta C, which is the critical angle. Okay, and in this case we get a reflected ray as well. Okay, the ray denoted by the red arrow here is the reflected ray. Okay, and this angle theta r, theta small r, is the angle of reflection. Okay, I've noticed something in your book that I'll have to show to you. In this book, it is written that this is the refracted ray. Well, it's not the refracted ray. Okay, what is the condition for refraction? The refraction definition says when an incident ray strikes on a surface of another medium or the two mediums, it gets its angle changed and starts traveling in another medium. But you can see here, this ray does not start traveling in another medium. It just starts traveling in the glass in this case, but it gets just deflected from its original path. Okay, so this is not a refracted ray, this is a reflected ray. I don't know why they've put a refracted ray over here. This word shouldn't be here. This should be reflected ray. This should be reflected ray. Okay, I'll tell you why later. Okay, so first we'll just continue with our figure B. Okay, now you understand if the incident ray falls on the point of incidence with such angle so that the refracted ray makes an angle theta r equals to 90 degrees, then we will get another ray which would be reflected back into the same medium with an angle theta r, and this angle would be equal to the angle of incidence or critical angle. By the definitely it's the law of reflection of light, so both the angles are the same. Okay, so what is this critical angle? How can we find it out? Sorry. To find it out, we're going to use the Snell's law. The Snell's law says that sorry, the refractive index of the first medium. In this case, which one is the first medium? This is the first medium, okay, because incident ray is traveling in this medium. This is the first medium, this is the second medium, okay. Refractive index of the first medium multiplied by sine of angle of incidence, or the angle or the critical angle, is equal to the refractive index of the second medium into the angle of refraction in that medium. Pretty simple. Now, angle of refraction, we have given that in this case is 90 degree. We already know that. Putting sine 90 degree over here, the rest of the things remains the same. And I sine theta c equals to n2. Sine 90 equals to 1, so we have not put it here. Okay, so we can also write this equation as this. We're gonna just divide it when multiplied with sine theta c. We will divide it by n2 if you take it to the other side of the equality. So this is the equation that we will get finally. And from this equation, we can actually calculate the theta c, the critical angle, if we know the refractive index of second medium and the refractive index of the first medium. Knowing these two quantities, we can calculate the critical angle for the incident ray. Okay, so this was the case with the critical angle. Remember, we have not reached the total internal reflection yet. Okay, we will see it in the figure number C, the figure C. If the angle of incidence increases or becomes greater than the critical angle, what happens? Okay, we know that increasing the angle of incidence increases the refracted angle. Okay, but when it reaches 90 degree, when this refracted ray is on the surface of these two mediums, what next? How much can it be increased? If it increased furthermore, this refracted ray would just travel in the medium itself, in the first medium again. Okay, so if we increase the angle of incidence more than the critical angle, then total internal reflection would occur. Okay, in this case, this is the incident ray and the angle of incidence is greater than the critical angle. So here we can see the ray will be reflected back into the same medium with the same angle theta r as that of the theta I, or the angle of incidence. So here we can see a pure reflection phenomena occurring. Okay, so there are two basic conditions that needs to be fulfilled for the total internal refraction of light. Okay, so these two conditions are that the light must travel from an optically denser medium. What is an optically denser medium? Okay, in this case, glass is optically denser medium. Why? Because in this case, the refracted ray will be moved be moved away from the normal. So in this case, and in the case of glass, it would be moved towards the normal. Okay, so in this case of glass, if it's moved towards the normal, then glass will be optically denser medium. And in the case of air, the refracted ray would just move away from the normal. So this would be optically less dense medium. Okay, now this is the total internal reflection of light, and we have studied the first condition, which is light must travel from an optically dense medium into an optically less dense medium, of course. The second condition is that the angle of incidence must exceed the critical angle associated with the material. So, as I told you earlier, the angle of incidence must exceed the angle, the critical angle in this case. So, in this case, theta I is greater than theta C. Okay, theta I must be greater than, not equal to. Okay, not equal to. If it's equal to the theta C, then what would happen? We will have a refracted ray, of course. Okay, so the total reflection, the total internal reflection, for the total internal reflection of light in the same medium, we don't need this refracted ray over here. Okay, we need complete reflection in the same medium. Okay, so this is the second condition for the total internal reflection of light. Okay, so this was all in it. Moving to our second topic, which is optical fibers. Okay, this is pretty easy topic. First, I'm gonna ask you a question. Okay, if I try to just introduce a ray of light in a glass rod, this is a glass rod, and if you try to just shed light on it in this direction, what would happen? Okay, normally the light was just come to this point and gets reflected to the same medium, or it would get, some of the part would get refracted over here, but after refracted it would again just leave this medium and just travel towards the air after refraction, after refracting again. Okay, so optical fibers in this case are the application of the total internal reflection of light. How? I'm going to show you how. When the ray of light enters this glass rod, we can take plastic rod or glass rod. These rods are basically very thin. They have a very small diameter, even smaller than your hair strand. Okay, so in this case, what happens when light enters this rod? It gets refracted and strikes the surface with an angle which is greater than the critical angle in this case, and the critical angle for these two mediums, and it just gets refracted. It gets totally internally refracted over here. Okay, none of the part gets to the other side of the medium, other side of the glass rod. Okay, so in this case, light would continue to travel like this. It would just keep reflecting like this. Okay, till it just reaches to the end. Okay, after reaching the end, it will just escape from the glass rod. Okay, so this is the basically application of total internal reflection of light. So optical fibers are flexible, of course. These are not just you can say rigid glass rods. These are flexible and they have curves. In this case of curves, the light would just enter from this point, strikes the surface, and gets reflected back. Okay, because this is internal reflection. And the condition for the total internal reflection in this case is fulfilled because this angle, if we just draw it the normal here, this angle would be greater than the critical angle of the medium. Okay, so in this case it just gets reflected and reflected back and reflected and strikes the surface and reaches its end. Okay, so basically studying optical fibers. What are optical fibers? Optical fibers are some strands made of glass or plastic or any transparent medium through which light can travel, and it has three parts. Okay, this is the core. Okay, so what exactly is a core? The core is the central part of the optical fiber, which is actually made of glass, and it actually plays part in the total internal reflection. Okay, so this is the central part of this wire or this fiber, which actually plays the role of internal reflection. Now, you might notice that here is a gap between this line and this line. Okay, so this whole line is called the cladding. This is called the cladding. Okay, so what exactly is a cladding? Cladding is just you can say a covering or an insulation provided to the core. Cladding is provided so that we will have a medium other than the glass, the core itself. Okay, so cladding is also made of glass or just plastic and any kind of transparent medium, but it has properties different than the core, so that these 1 and 2, these two medium will have different properties, so that the light striking this point won't just start to travels in a straight line and it would get refracted. Okay, so in this case the core would be optically dense medium and this would be optically less dense medium. Okay, so this is why we apply cladding to the optical fibers or optical fiber wires. These are actually a kind of wire. Okay, now coming to the third part. Third part is the jacket. What is the jacket? As the name suggests, it is the outermost layer on the wire. It is made of an insulator. An insulator for the protection of the wire from just scrambling or being bent, or it just protects from further attenuation. Attenuation means that from disturbance by light coming from outside of the wire, it protects this wire from that. Okay, so jacket is basically the outermost layer of the wire for the external protection, from the protection from external influences. All right, so in one jacket there could be more than one claddings. Okay, for example, we have a jacket over here and it has 3 claddings. Okay, you might have seen it in the wire in your house. Like this is the cladding. This is the bundle of the wire inside it. Okay, these are the bundle of wire inside the cladding, and this is the outermost jacket, which protects us from the internal influences. Okay, thank you so much everyone. If you have any question, you feel free to ask me. Thank you so much.